So good morning everyone and welcome to this lecture. This is lecture number 5 in electrostatics and we'll be dealing with electric potential in this particular session. What do you mean by electric potential? Well, in the previous class we have dealt with electric field. We have dealt with Gauss law. We are done with Gauss law, electric field lines, and so on. Now we'll move on to this electric potential. Now, before moving on to electric potential, we will go through this electric potential energy or electrostatic potential energy, and everyone would know the meaning of electrostatic potential energy. This electrostatic potential energy is similar to something that we have already done. What? What we have done? This electrostatic potential energy is similar to what? What we have done?
Gravitational potential, sir.
Huh? Electrostatic potential energy is similar to what?
Gravitational potential, sir.
Gravitational potential energy. If you move any body of mass m in a gravitational field, work is done by gravitational forces. Similarly, if you move a charge, let us say this is a point A and this is a point B, and you move a charge on any path, if you move a charge along any path from point A to point B, if you move this charge along any path from point A to point B, I am moving a charge from point A to point B. In an electrostatic field, work is done by electrostatic forces. This work done by electrostatic forces, electrostatic field or electrostatic force, electrostatic force. What type of force is electrostatic force? Electrostatic force is a conservative force. Do we remember this? Electrostatic force is a conservative force. That means work done by electrostatic force. Work done by electrostatic force. Let me write it as work done by E. Electrostatic force. It does not depend on what? It does not depend on path. Work done by electrostatic field or electrostatic force does not depend on path. In fact, you can write this work done by electrostatic force as negative of change in electrostatic potential energy. Work done by electrostatic force can be written as negative of change in electrostatic potential energy, or I can write it like this: work done in moving a charge from A to B by electrostatic force will be negative of change in potential energy in moving from A to B. Negative of change in potential energy means final energy minus initial energy ka negative. That becomes initial energy minus final energy. We have already seen it in gravitation. This is just a repetition of what we have seen in gravitation. This is known as the electrostatic potential energy, or the difference in electrostatic potential energy between the 2 points, or the change in electrostatic potential energy between the 2 points. The change in electrostatic potential energy in moving from point A to point B is nothing but negative of work done in moving an object, not an object, in moving a charge from point A to point B by electrostatic force. So you can also write it like this: F dot dr is the negative integral from A to B. Do we understand this, or this has gone above our head saying bye bye?
We understood, sir.
This will be equal to UB minus UA. There is a different ways in which you can write this. The more the number of ways you understand, the better it is for you. I'll give you 2 minutes to note this down. Then let's move ahead and see some properties of this, or some important points about this electrostatic potential energy. We already know it. We'll just note them down in point-wise fine. Electrostatic potential energy of any body or any system of a body is a scalar quantity. The scalar quantity, like work done, it can be positive, it can be negative, it can also be zero. The SI unit of this electrostatic potential energy will be same as all energies, which is nothing but same as work. Sometimes this electrostatic potential energy is also given in terms of electron volt. 1 electron volt is 1.6 into 10 raised to the power minus 19 joules. You must understand this. The next thing that you must understand is absolute value of electrostatic potential energy is not defined. It is not defined what is the absolute value of electrostatic potential energy. Only change or difference in electrostatic potential energy is defined. Only change in electrostatic potential energy is defined, because to define absolute value, you need to define a point whose electrostatic potential energy, or define a system whose electrostatic potential energy can be taken as zero. Do we understand this? So, electrostatic potential energy depends on the reference point. Do we understand this? If you remember, gravitational potential energy at infinity, it was taken as zero. Do we remember this? Similarly, electrostatic potential energy depends on the reference point. In most of the cases, electrostatic potential energy, when the bodies are separated by infinite distance, is taken as zero. Do we understand this? Do we understand this?
Yes, sir.
Electrostatic potential energy is defined for a system of particles. For a single particle, if it is placed in an electric field, that electric field is created by some other particle. So electrostatic potential energy is always defined for a system of particles. For a single particle, if there is only one charge in the universe, there will not be any electrostatic potential energy. Do we understand this? Electrostatic potential energy is always defined for a system of particles. Do we understand this?
Yes, sir.
For a single point charge, there is no electrostatic potential energy. For a single point charge, there is no electrostatic potential energy. Now, this electrostatic potential energy for a system of charges. Have you noted this down?
Yes, sir.
Now, this electrostatic potential energy for a system of particles or a system of charges can be defined in two, can be of two types, can be defined in two different ways. It could be defined as interaction energy between charges of a system, or if there is one body, we can define it as self energy of a body. So electrostatic potential energy can be thought of as two types. It could be interaction energy between particles, it could be self energy of a charged object. Well, they are not different, they are actually same. This electrostatic potential energy is coming because of interaction of these particles. If there are particles, they will interact with each other. Because of this interaction between the two particles, this electrostatic potential energy comes. Do we understand this?
Yes, sir.
Then we can have the next heading, electrostatic potential energy for a system of 2-point charges. Electrostatic potential energy for a system of 2-point charges. If I have a system of 2-point charges, here are the 2-point charges Q1, Q2, separated by a distance of r. We have already discussed gravitational potential energy of a system of two masses. Similarly, you have electrostatic potential energy for a system of 2-point charges. What will be the electrostatic potential energy? Remember, the first point is always absolute value is not defined. The absolute value is not defined. What is defined is always the change or the difference. Now, to define absolute value, you need a reference point. Reference point is taken as infinity. What do you mean by reference point taken as infinity? When the 2-point charges are separated by an infinite distance, the potential energy of the system at infinity is taken as 0. That means if one charge is here and the other charge is here, Q1 and Q2, they are separated by a very large distance equal to infinity, then the energy of the system is taken as 0. Do we understand this?
Yes, sir.
So, if I take the energy of the system, what is my system here? My system here is 2-point charges. My system here is 2-point charges, Q1 and Q2. When these point charges are at infinite distance from each other, if I take that condition as the condition of 0 energy, then I can define the potential energy of these 2-point charges when they are separated by a distance of r. When they are separated by a distance of r, their potential energy can be written as K Q1 Q2 divided by r. Where what is K? K is 1 by 4 pi epsilon naught. I can write it as U12, energy of the point charge 1 2 system. Energy of the point charge 1 2 system is K Q1 Q2 by R. K Q1 Q2 by R. That will be the potential energy of this system of 2 point charges when they are separated by a distance of R. Remember, here I have assumed what? Potential energy when they are at infinite distance from each other is taken as 0. Do you understand this?
Yes, sir.
This is the potential energy of a system of 2 point charges. Now, this potential energy, if charges are like, this potential energy would be positive. If charges are unlike, one is positive and the other is negative, then this energy will be turning out as negative. Do you understand this?
Yes, sir.
Like charges, two positive charges, energy is positive. One positive and one negative charge, interaction energy of those 2 point charges, the system of those 2 point charges would be negative. Do you remember what was the electrostatic potential energy of a system of 2 point masses? What was the electrostatic potential energy of a system of 2 point masses? No one remembers it as expected. There's nothing new in this. Potential energy, yes?
G M1 M2 by R.
Potential energy of a system of 2 point masses minus G M1 M2 by R. The most important aspect, which you have obviously forgotten, and there is nothing new in this, is the negative sign. Gravitational potential energy is always negative. Anyways, I'll give you 2 minutes to note this down. This is the next question. You have to find the electrostatic potential energy of this system. You will assume that when these charges are infinite distance away from each other, the potential energy of the system is 0. If in that case the potential energy of the system is 0, now they are arranged at 4 vertices of a square of edge length A. What is the potential energy of this system? I'll give you a minute to give me the answer. Any idea how you're going to do this? If no, there is no idea, there is no point of wasting time. We don't have time. Do you have any idea of how to do this? Do we have any idea how to do this? Do we have any idea how to do this?
Sir,
Yes.
is it minus root 2 KQ square by A?
Okay, so how are we supposed to do this? We are supposed to find out how many pairs are there. This is pair number 1. We know the electrostatic potential energy of 2 point charges. This is pair number 1. This is pair number 2. This is pair number 3. This is pair number 4. 4 pairs like this. Then you have the 5th pair between these two, and you have the 6th pair between these two. You have to find the energy of each pair and add them that will be the energy of the system. What will be the energy of the system? So 4 pairs of there separated by a distance of a. So 4kq square by a. I don't know from where you are creating this negative charge, negative sign. God knows which universe you are wandering in. Please come back to the universe. This is a good universe to live in. Plus, there are 2 pairs which are separated by a distance of a root 2. So that is the answer, 2kq square by root 2a. This is how we find out the electrostatic potential energy of this system. This is exactly same what we had done in gravitation, but obviously you don't remember it, so there is no point of telling you all those things because we don't remember it. Since we don't remember it, there is no point of going back to all those stupid things in life, right? They've already done all these things. But obviously we don't remember. So there is no point. Just for the sake of argument, just for the sake of argument, this is the question that was done way back, some 3-4 months back. See, and the problem is you've already given one attempt this year, 2 attempts last year, and we are all blank. We don't remember anything. What to remember? Why should I remember? And I told you also, I'm not doing gravitation. I'm doing gravitation here. We'll be repeating everything here. And that's why I'm not doing electrostatic after gravitation, because if I do it, you will forget everything. So that's why I'm giving you some time so that you can remember something. There's no point. Whatever I do is all going to go down the drain in the drains of Hyderabad, and I'm filling up the drains of Hyderabad. And the municipal corporation of Hyderabad would be looking for me. Who is this person who's filling up the dirty drains of Hyderabad with all these non-worthy things in the universe? I am wanted man in Hyderabad because I'm filling up the drainage system of Hyderabad with everything down the drain. Everything goes down the drain. Anyways, as I keep on telling you, what students are like cash vouchers. Always redeem yourself. So the next question that I'm going to ask, if there is any problem, if there is any hope, what is the work done in assembling this system? What is the work done in assembling this system by the electrostatic force? How much work is done in assembling this system by the electrostatic force? And I'll give you 1 minute. Get me the answer. What do you mean by assembling this system? Assembling this system means bringing all these charges would be at infinity. All these charges would be lying at infinity. So work done in assembling this system means work done in moving all these charges from infinity and making it into this system. So from infinity to system by the electrostatic force. So that can be written as U at infinity minus U of system. This is how you write it. U infinity is 0 minus U of the system. You have already calculated the energy of the system. So negative of that energy of the system will be the work done in assembling this system by the electrostatic force. I know you have given the same answer, but you just given the answer without knowing what is to be done. So this is how it has to be done. Because there could be one more work done, I could have asked this question, what is the work done in assembling this system by the external force? In that case, what would have been the answer? So work done in assembling the system by an external force would be work done from infinity to system by the external force, and that work done can be written as U system minus U infinity final minus initial. Here we are assuming that the change in kinetic energy is 0. I hope I have made you understand this point some 2 months back as well. So in that case, that work will be the energy of the system. That is the work done in assembling this system by the external force. Do we understand this?
Yes, sir.
Now I have this system. I have a Q1, positive Q1 charge, which is fixed at some point in space. And I have a negative charge, which is placed at infinity. Very large distance at infinity, it is put. This charge can move. This negative charge can move. What will happen to this negative charge? Will it remain here? We'll just chill out here. I am chilling out. I have cleared JEE. I'll chill out in IIT. Will it remain here? Chilling out? Or something else? Then I think it will chill out. And we don't know why will we are not charges. We are not related to this charge. Why will we know?
It will move towards Q1, sir.
It will move towards Q1. See, God exists. I always start believing that God doesn't exist, but then I am made to realize that God exists. Yes, God exists. And this charge will move towards this charge, the fixed one. So minus Q charge moves here. When it is at a distance of R from the original fixed charge, it will have some velocity V. Yes or no? It is experiencing a force. It will have some velocity V. Yes or no?
Yes, sir.
We have to find out that velocity. How much is that velocity? Sir, how will we know? We are not charged. We are not Q1, Q2. And we don't know physics. How will we calculate? Anyways, we can always try. And I am giving you 2 minutes to try. So how are we supposed to do this? There are two ways in which I can do this. The first way is by applying my favorite work energy theorem from infinity to Let us say point A, this is infinity. From infinity to point A, what does this work energy theorem state? It states that work done from infinity to A by all forces should be equal to change in kinetic energy. The only force which is working here, I have not talked about their masses. Let us say that the mass of this body is m, and there is no gravitational force here. The only force that is acting is electrostatic force. So the only force acting here is electrostatic force. So work done from infinity to A by electrostatic force will be equal to change in kinetic energy. Final kinetic energy is half mv square and the initial kinetic energy is 0. Now work done from infinity to A by the electrostatic force can be written as energy at infinity minus energy at A, that will be equal to half mv square. Do we understand it up till here?
Yes, sir.
Energy at infinity when they are separated by infinite distance is 0. Energy at point A is minus k q1 q2 by r. So minus of that will be k q1 q2 by r. K q1 q2 by r is equal to half mv square. From here you can find out the speed at point A. This was one way. If you don't want to do it this way, you can do it by lock me. What is lock me? Law of conservation of mechanical energy applied from infinity to A. It says that total energy at infinity should be equal to total energy at point A. The total energy at infinity, the potential energy at infinity is 0. The kinetic energy at infinity is 0. So 0 must be equal to potential energy at point A is minus k q1 q2 by r. Kinetic energy at point A is half m v square. Whether you do it in this way or you do it in this way, you will end up with v. V will be equal to 2 k q1 q2 by r ka under root. And that is the answer that I was looking for. I missed one m. M will come here. And that is how any question of this nature has to be done. Do we understand this? I'll give you 2 minutes to note this down. And we move ahead and we write the heading electrostatic potential or electric potential difference. Electric potential or electrostatic potential or electrostatic potential difference denoted by the letter V. What is this electric potential or electrostatic potential difference between 2 points? I have one point A, another point B in an electrostatic field. We have moved a charge from point A to point B in any path. We know that the work done does not depend on the path. Yes or no?
Yes, sir.
Now, how do I define the potential difference between the points A and B? The potential difference between the points A and B, VA minus VB. The potential difference between the points A and B, VA minus VB, is defined as UA minus UB per unit charge. Whatever charge we have moved, how much is the change in energy per unit charge? That is defined as the potential difference between the 2 points. That means it will be equal to work done from A to B by the electrostatic force per unit charge. Potential difference between 2 points A and B in an electrostatic field is nothing but change in energy, or the difference in energy per unit charge, or the work done by electrostatic force from A to B per unit charge. Do we understand this?
Yes, sir.
From here, you can also write the formula in this way: UA minus UB will be equal to Q into VA minus VB. Do you understand how I have written this? Do we understand how I have written this?
Yes, sir.
Note this down. I'll give you 2 minutes. There are some things that you must remember. The first thing is potential, electrostatic potential or electric potential. It's a scalar quantity. It may be positive, it may be negative, it may also be zero. Do we understand this? Yes or no?
Yes, sir.
The SI unit, the SI unit of electric potential difference or electrostatic potential difference is volt. 1 volt is 1 joule per coulomb. Do we understand this?
Yes, sir.
Remember the dimensional formula: M1 L square T minus 3 I ampere current minus 1. Also remember, absolute value of potential difference or absolute value of electric potential is not defined. There is no definition for absolute value of electric potential. The absolute value of electric potential is not defined. Then what is defined?
Change in potential and potential is defined.
Change in potential or difference in potential is defined. Change or difference in V is defined. For reference, we have to find a point whose potential can be taken as zero. For reference, potential at infinity can be taken as zero. Do we understand this?
Yes, sir.
For reference, potential at infinity is taken as zero. If you take potential at infinity to be zero, then you can define the potential of all the points in the universe. Do we understand this? First listen to me, then I'll give you time to write. Do we understand this?
Yes, sir.
If you want to define electric potential, it is negative of the work done by electric field. I have already told you that. Electric potential is a scalar quantity. Potential at infinity is taken as zero. Therefore, the potential created by a positive charge will be positive and potential created by a negative charge would be negative. Do we understand this? We're talking about electric potential. Remember, there is a difference between electric potential and gravitational potential. Gravitational potential is always negative. Electric potential of a positive charge is positive and a negative charge is negative. Do we understand this?
Yes, sir.
The next 2 points, we will also see them. Don't worry. But first, write them. Potential decreases in the direction of electric field, or I can say it in a different way. Electric field always flows from a point of higher potential to a point of lower potential. I had given you this point in the last class. Yes or no?
Yes, sir.
If you have more than one charge, then if you want to find out the potential at any point, you simply add you simply need to add all the potentials. Potential is a scalar quantity. You can add them just like numbers, and therefore finding out the potential is very easy compared to finding out the electric field, because electric field is a vector quantity. You have to look for direction. Potential is a scalar quantity. You don't have to look for direction. You can find out the potential very simply by adding plus and minus. Yes or no?
Yes, sir.
I'll give you 2 minutes to note it down. Okay, then, so we have seen the relation between potential and potential energy. We have seen the relation. Let us see the use of potential. I have seen this formula come many times in many different ways. So you can note it down. Now, sometimes what we have seen is it is given that an electron or a proton is accelerated by a potential difference of V. So you can note this down. If a charge is accelerated by a potential V, then its kinetic energy half mv square will be equal to q multiplied by V, because whatever energy or whatever work is done, that energy or work done is converted into kinetic energy of that charge. So from here you can find out the speed of that charge. The speed of that charge will be 2qv by m ka under root. Do we understand this?
Yes, sir.
So remember this. I don't know whether how long you will remember this, but next session is just around the corner. I hope you can recollect it up till that point, 1 month or 2 months from now. Now, this concept of electric potential can also be used to calculate the work done and the potential difference and all that. If you understand this, let us solve this question. A charge of 2 microcoulomb is taken from infinity to a point in an electric field without changing its velocity. Work done against electrostatic force is minus 40 microjoule. What is the potential at this point? Such questions are coming these days, and if you recollect and if you remember and you understand that whatever questions we do in the class, same questions will appear in your examination hall. I don't have to give you enough proof of that, because I've given, you have also seen the paper yourselves and you would have found out the same thing on yourself. So please do the questions. If you can't do any other question, if you simply do the question that we do in the class, that will be good enough to clear your JEE in the last attempt that is remaining probably for this year. and I hope that you would be doing it. Just to tell you, this was a question that we did on the class, I think on the 29th of January. This I asked you to find out the electric field at point A, B, and C. Do you remember this question?
Yes, sir.
See, I just saw this question yesterday while I was looking at the paper of 1st of February. This is the paper of, where is that? And I hope you see this paper. This is the paper of 1st of February. We have not done this. We have not done this. Magnetic field. We have not done this. De Broglie wavelength. We have not done this. Executing SHM. I think we have done enough question on this. See, two non-conducting sheet having charge entry sigma sheets are parallel to the. See, exact question. Exact. This one.
Yes, sir.
Just 2 days afterward it came in the exam. Just 2 days afterwards. Same. I gave you all the 3 points. The only difference between my question and this is here they are both positive. In my question was one positive and the other negative. I had also given you 2 points, 3 points. So the moral of the story is if you just do what happens in the class, you should be doing good enough. But I don't think that you are doing it. And that is a concern. That was the question, and this was the question that we did. Anyways, so whatever we are going to do now may be coming in the paper 5 days. The papers are over for this session, but in the April session, the same question might be coming. You never know. And I don't look at the question and then do a question. I know what questions are going to come. This is probably the next question that is going to come in the next session. So a charge 2 microcoulomb is taken from infinity to a point in an electric field without changing its velocity. If the work done against electrostatic force is minus 40 microjoule, what is the potential of that point? You have 2 minutes to give me the answer. So the answer is 20 volt. 20 volt? Yes or no?
Yes, sir.
Answer is minus 20. So you get minus 5. Whether you should have got plus 4. You got minus 5. Remember the question. What is the question giving you? The charge is moved from infinity to a point. So work done in moving it from infinity to this point A without changing its velocity. So it is moved very slowly. Work is done against the electrostatic force. Work done against electrostatic force means this is the external work that they are talking. Work done in moving it from infinity to A by external force is given, which is U infinity minus UA. No, this is the work done by the external force, so it is reverse. So it is, if you make a simple mistake, the answer will be completely different. This will be equal to Q times VA minus V infinity. Now you will get the correct answer. potential of point A will be minus 20 volt. Minus 20 is the answer, not plus 20. I'll give you 2 minutes to note this down. I'll again write it. All the formulae that we have done. Work done from A to B by electrostatic force is UA minus UB, and that can be written as charge which is moved into VA minus VB. Work done from A to B by external force, that will be how much? See, I don't know. UB minus UA. What is the use of writing all this when you don't understand it? You write it very quickly, just are done. But then you're not able to tell me. So what is the point? Q times VB minus VA. But this formula is only valid. This formula is only valid when the change in kinetic energy is 0. Take a deep breath, take your time, understand it, then tell me when you are done. Let's move ahead and let us now write the formulae for electric potential due to different type of charge distribution. Now remember, whatever formulae we are writing, you must understand that potential at infinity in most of the cases is taken as 0. In one or two cases, we cannot even take infinity potential as 0. We will come across those cases. But in all the other cases, potential at infinity is taken as 0. If potential at infinity is taken as 0, we are going to write the formulae for electric potential due to different type of charge distribution. What is the first type of charge distribution? The first type of charge distribution is a point charge. Electric potential due to a point charge. Electric potential due to a point charge. And this is a point charge. We have a point P at a distance r from this point charge. Now we have already calculated the electric field due to this point charge at this point. How much is the value of electric field? No one remembers electric field also. The value of electric field is kq by r square. That is the value of electric field due to this point charge. And this electric field due to this point charge is moving in this direction. This is the direction of your electric field. This is the direction of your electric field. Electric field is moving like this. Your electric field is going like this. This is the direction of your electric field. The potential at this point P The potential at this point P is given by the formula KQ by R, where K is 1 by 4 pi epsilon naught. I hope you understand this. Yes or no? No or yes?
Yes, sir.
Okay. Now, electric field is going from positive charge away from a positive charge. If I take 2 points, let us say point A and point B here. Point A and point B here. Remember, this is a positive charge. Point A and point B here. If I call the potential of point A as VA, and if I call the potential of point B as VB, remember potential at infinity is taken as 0. Which point is at a higher potential, point A or point B?
Point A.
Which point is at a higher potential, point A or point B?
Point A.
Point A. An electric field is going from which point to which point?
From A to B.
That means electric field always moves from a point of
Higher potential to lower potential.
higher potential to lower potential. Now, if I make this charge as negative, electric field would then be going like this. Yes or no?
Yes, sir.
Again, I make 2 points. This is point A and this is point B. Potential at point A is VA. Potential at point B is VB. Remember, the charge is negative now. Which point is at a higher potential, A or B?
B, sir.
B is again at a higher potential. That means whether it's positive charge, whether it's negative charge, electric field lines are always going from a point of higher potential to a point of lower potential. Do we understand this?
Yes, sir.
Oh, this has gone above our head. Saying bye bye.
We got it.
Now, sometimes they may give you a question where the two charges are the distance between the charge and the point is filled with dielectric. Sometimes they might give you, just to confuse, two dielectrics, and I had given you the formula of one dielectric, and in the first session the question came from the dielectric part. Yes or no? So if the question is like this, the most difficult question, where the distance r is filled with two dielectrics, one dielectric with thickness T1, dielectric constant K1, other dielectric with thickness T2, dielectric constant K2. These are the formulae for potential and electric field. Do we understand this? Oh, this has gone above our head. Saying bye bye, bye bye, bye bye. I'm going bye bye.
We understood.
I'll give you 2 minutes to note this down. Then we move ahead,
Yes, sir.
and on the same thing, we can draw these are the graphs of electric potential due to a positive charge and negative charge. The charge is placed at the origin. You can see how the potential varies. Do we understand this?
Yes.
Similar to this, you can have a system of two positive or two negative and a positive and negative charge. How does the potential vary? You can see this in the other two diagrams which are drawn. All these graphs are very important. I've seen a lot of questions coming on graphs and this. One of these questions may land up in your next session. I'll give you 2 minutes to note this down. Then let's move ahead and move on. The next thing is due to a rod. Due to a rod. And if you have a rod like this, and you have to find the electric potential at the point P. Electric potential at the point P is given as K lambda natural log of R plus L divided by R. So just remember this formula. I have not seen this formula come anytime. This is just for your, if it comes ever. This is the electric, this is the potential if the rod is like this. If it is like this, oops, where is this? If the rod is like this, we have seen that electric field will be given by these formulae Ex and Ey. It will have both X and Y components. Do we remember this? This question should not come. It will only come in case of an infinite rod. But still, do we remember this electric field formulae?
Yes, sir.
Remember this? Now, this is the formula for electric potential. Again, this formula will not come. I've not seen any question come here, but just for the sake of writing it, I'm giving you this formula, and again I'm giving you the formula for an infinite long conductor as well. Now for an infinite long conductor, this is the conductor where V infinity cannot be taken as 0 because this conductor is infinite, and therefore the absolute value of potential is not defined. Therefore you see this C here. Do we understand this C? The C tells us that the absolute value is not defined. We don't know where the 0 is. Everyone got this? Yes or no? No or yes?
Yes.
I'll give you 2 minutes to note this down. Then we move ahead and we move on to ring. At the center of the ring, the potential is not 0. Electric field is 0, but the potential is not 0. The potential is KQ by R. And a question based on this came in this session between potential and electric field. Potential is KQ by R. If it is positive, it will be plus KQ by R. If it is negative, it will be minus KQ by R. Do we understand this?
Yes, sir.
At any point on the axis, it will be kq upon under root of r square plus x square, depending on where is x. This is the graph. Graph is very important. At the center, it is maximum kq by r. If it is positive, then it is maximum. If it is negative, then it is negative maximum. Do we understand this?
Yes, sir.
One thing you must note that potential does not depend on this potential does not depend on distribution of charge. This potential does not depend on distribution of charge. Here we have taken this ring to be uniformly charged. If it was not uniformly charged, if one side you had more charge and other side you had less charge, that will affect the electric field, but the potential will remain same because all the points are at the same distance, so it does not depend on the distribution of charge. Do we understand this?
Yes, sir.
Pakka? Everyone understands this? I'll give you 2 minutes to note this down. Then this is the electric potential due to a disk, and due to a disk you can see the electric potential is sigma by 2 epsilon naught into under root of r square plus x square minus x, and this is the graph. Do we understand this?
Yes, sir.
Note it down. I'll give you 2 minutes. Then we move to this infinite sheet. Infinite sheet electric field plus sigma by 2 epsilon naught. Do we remember this?
Yes, sir.
If the point is at a distance r, the absolute potential is not defined because this is infinite sheet. I cannot take infinity point as 0. So it is defined like this. Potential difference is defined only minus sigma r by 2 epsilon naught plus c. The c tells us that I don't know the point whose potential is taken as 0. Do we understand this?
Yes, sir.
I'll give you 2 minutes to note this down. Then we come to this one, conducting sphere and conducting non-conducting shell. The charge is only on the outer surface. Do we understand this? Yes or no?
Yes, sir.
Electric field outside is kq by r square. Do we remember this formula? Yes or no?
Yes, sir.
It is same as the point charge. Yes or no?
Yes, sir.
Formula for electric potential is also same as potential due to a point charge. We understand this? Yes or no?
Yes, sir.
On the surface, the formula becomes on the surface, electric field on the surface, the formula becomes kq by r square. Yes or no? Electric potential on the surface becomes kq by r, capital R, capital R. Do we understand this? Electric field inside is 0, electric field at the center is 0. Do we understand this? Do we remember this?
Yes, sir.
Potential inside is kq by r, potential at the center is kq by r. That means potential remains constant when electric field is 0. Potential does not change. That is what you need to remember. What you need to remember, when potential, when electric field, when electric field is 0, potential is not 0, but potential remains constant. Will you remember this?
Yes, sir.
Do we understand what I have said?
Yes, sir.
Yes or no? No, yes.
Yes, sir.
Pakka na sir?
Yes.
You're pakka looking like kacha. Pakka?
Pakka, sir.
Now I have shown you both the graphs. One of this graph came in one of the sessions here between V and R, this one. You can see E inside is 0, but potential is not 0. Potential is constant. Do we see this? Constant potential. Do we see this? Potential is constant. Do we see this red line?
Yes.
Potential is not 0, but here electric field is 0. Do you see this? Just gone above our head, saying bye bye. I'm going, sir. Bye bye, sir. 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 Give you 2 minutes to note this down. Then we come to non-conducting sphere. Non-conducting sphere, the Charge also comes in the volume. Electric field outside is same as due to a point charge. Do we remember this?
Yes, sir.
Potential is also same as potential due to a point charge. Do we understand this?
Yes.
This is outside. This is on the surface. Electric field is maximum. Do we remember this?
Yes, sir.
Electric field inside. Now potential on the surface is kq by r. Maximum. Inside, I'd also given you a formula of gravitational potential. I don't know. I know that you don't remember it. This is the formula for electrostatic potential. On the center, the potential is 3 by 2 times the potential of the surface. Do we understand this?
Yes.
Magnitude wise, it is 3 by 2 times. If it is positive, it will be plus. It is plus 3 by 4 times. I mean, 3 by 4 positive. If it is negative, it is 3 by 4 minus. Do we understand this?
Yes.
These are the two graphs for electric field and electric potential. Put all these two graphs so that you are able to understand everything together. So these are the graphs, these are everything. I hope you can note this down fast. Then you can take down these two formulas as well. Due to a semicircular ring at the center, kq by r, whether it is a semicircular ring or a quarter ring or whatever, it will be always kq by r. Whether it is uniform ring or non-uniform ring, it will be always equal to kq by r, because the distance of all the points from the center is same. Do we understand this?
Yes, sir.
Hemispherical body, I have told you the electric field is sigma by 4 epsilon naught, potential is sigma r by 2 epsilon naught. Again, we have assumed that the potential at infinity is 0. I'll give you 2 minutes to note this down. Then this is the same thing written in a tabular form. Point charge, potential is kq by r. Potential at infinity is 0. And this is the graph. For a ring, uniform or non-uniform, at the center kq by r, at any point kq upon r square plus x square. This is the formula. Uniformly charged conducting or conducting sphere or conducting or non-conducting shell. This is the diagram. We understand this, yes or no?
Yes.
I'll give you 1 minute. This is in a tabular form. If you have missed any point, you can note it down. I'll give you a minute. Then these are the remaining three. Uniformly charged or solid sphere, non-conducting. This is one. Remember, in place of K, if you put G, and in place of Q, if you put M, this becomes the formula for gravitational potential inside the earth. Do we remember this?
Yes, sir.
Infinite line charge, absolute value is not defined because you cannot find a point where potential is 0. Therefore, the potential difference you can calculate from this formula or this formula here. Do we understand this? I'll give you 2 minutes to note this down. This is the next question. You have to find, there is a system of two positive charges, plus Q and plus Q, kept like this. You have to find the potential of point O, you have to find the potential of point A, you have to find the potential difference between O and A. Remember, potential at infinity is taken as 0. Do we understand this?
Yes.
Huh? 2 minutes you have. So, what is the potential at point O? Both the charges are positive.
2 kq by A, sir.
Both the charges are positive. They will create same potential. They will get added up. 2 kq by A. Yes or no?
Yes, sir.
Potential at point A is 2 times kq by root 2a. The distance is root 2a.
So it is root 2 KQ by A, sir.
To find out the difference, you just subtract O from A from O. Do we understand this?
Yes, sir.
So the question is pretty simple. If one charge was positive and the other was negative, then what would have been the answer? If one was plus Q and the other one was minus Q, then?
Sir, potential at A and potential at O would be 0, sir.
So A and O will come. In fact, all the points on this perpendicular bisector will have zero same potential, which is equal to 0. Yes or no?
Yes, sir.
But is the electric field 0? No, electric
sir.
field is not 0, but the potential is 0. So potential has got nothing to do with electric field. If potential is 0, that does not mean electric field is 0. If electric field is 0, it only means that the potential is same. Do we understand this?
Yes, sir.
Pakka?
Yes, sir.
This is the next question. Give me the answer first. So how are you going to solve this? Potential at point C will be K is K multiplied by 2. KQ by 6. Distance will be 6 minus K into 4 by 4. How much time you should take to do this? How much time do you need to do this? Sorry, the distance is 2, not 4. How much time do you need to calculate this? Potential at the point D.
2K by root 7 minus 4K by root 7, sir.
So 2K by root 7
Sorry, sir. Root 9, sir.
root 9 minus 4K by root 9. Root 9 is 3. So that is the answer. You should not have taken so much time. Do we understand this, or this has gone above our head saying bye bye?
Understood, sir.
What understood, sir? Simple question, not getting the answers after so much time, sir. No use, sir. Anyways, I always believe that students are like cash vouchers. Sometimes the cash voucher may not work, but that is not because the cash voucher is wrong. The code was put wrong. This is the next question for redemption. What is the potential at the center of the square? I'll give you 2 minutes to do this. The answer is 0. All the distances are same. A by root 2, A by root 2, A by root 2, A by root 2. Just have to find out the total charge. This is plus Q, plus 5Q, minus 5Q. The total charge is coming as 0. So the answer has to be 0 because everything else is same. Positive charge ka potential is cancelling out the negative charge ka potential. Do we understand this, or this has gone above our heads? Saying bye bye. Sir, I'm
Yes,
going. I'm going. I'm gone. Bye. Bye. Bye bye.
Understood, sir.
Understood, sir. What understood, sir? This was a question from IIT-JEE of 1998. You have this type of distribution. First charge is positive, second is negative, then negative, and it goes till infinity. What is the potential at the origin O? This is JEE of 1998. What is the electrostatic potential at the point O? You have 2 minutes to give me the answer. So what is the answer? The potential will be KQ by X into 1 minus half plus 1 by 3 minus 1 by 4 up till infinity. Do we understand this?
Yes, sir.
This is an infinite series. What is the sum of this infinite series? Natural log of 2. So that is the answer. KQ by X natural log of 2. This is an infinite log series. Do we understand this? Huh?
Yes, sir.
What, sir? If I would have changed the question and I would have made all the charges as positive, then what is the answer? Same question. But I have made all the charges as positive. Then what is the answer? Plus Q 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 plus Q. Huh? And no, I should not make the question like this. Not like this. I will put this question here. This question here because have you got this one? Yes or no?
Yes, sir.
Then do this one. Infinite charges are lying at 1248. It should be like this 1248 meter on x-axis, and the value of each charge is q. The value of intensity of electric field and potential at point due to these charges is respectively. The diagram is not given, but I will just show you the diagram so that you can do the question fast, because it is all about doing it fast. So this is the diagram. Do it fast, get me the answer and stay happy. Option A is the correct answer. To calculate electric field, all the electric fields are going in the same direction. So net electric field will be equal to KQ into 1 by 1 plus 1 by 4 2 square plus 1 by 4 square 16 and so on. This is an infinite GP. Yes or no?
Yes, sir.
You can find out the sum of this GP. If you have to find out the electric potential, this is KQ into 1 plus 1 by 2 plus 1 by 4 plus and so on. This is again a GP. The first GP is having common ratio of 1 by 4. The second GP is having a common ratio of 1 by 2. Do we understand this?
Yes, sir.
Yes or no? No, yes. Next question. Give me the answer fast. The potential at a distance x from the center inside a conducting sphere of radius r and charged with charge q is proportional to what?
Q by R, sir.
Q by r, because it remains constant. Do we understand this?
Yes, sir.
Remember this. Next one. The electric potential at the surface of an atomic nucleus. You have a nucleus whose atomic number is 50 and radius is 9 into 10 raised to the power 9 and 5. Rather than 9 into 10 raised to the power minus 15, it is misprint. 9 into 10 raised to the power of minus 15. Electric potential at the surface, atomic number is 50 and radius is 9 into 10 raised to the power of minus 15. What is the electric potential? I'll give you a minute to do this. Option B is correct. So how are you supposed to do this? Potential is K Q by R, where K is 9 into 10 raised to the power 9. Q is the total charge. How much is the total charge? So K multiplied by N, the atomic number multiplied by E. Right?
Yes,
Yes
sir.
or no? N is 50 and E is 1.6 into 10 raised to power minus
19.
Once you put this value, you should be able to get the answer. Yes or no?
Yes, sir.
This one, do it fast. 8 charges having the walls, not walls, values as shown, not walls, values. What is the electric field? No, not electric field. Electric potential at the center. Option A, you everything is same, all the distances are same. The distance of the charge from the center will be equal to, is already given, 0.4 meters. You just find out the total charge. How much is the total charge?
28 mu c, sir.
28 microcoulomb. You add positive, add negative, and then find the difference. Is it positive or negative? 28.
Positive, sir.
Positive 28. So K into Q by R, and that is your answer. Yes or no?
Yes, sir.
This one. Give me the answer fast. The answer is 0. I told you now. Positive charge, negative charge, perpendicular bisector, same charge, everything would be 0. Yes or no?
Yes, sir.
Do we understand this, everyone?
Yes, sir.
Next one, give me the answer first. A conducting sphere of radius r is given a charge q. Consider 3 points: B at the surface, A at the center, and C at a distance of r by 2. The electric potential at this point are such that.
Option B, sir. VA equals to VB does not equals to VC.
Take a deep breath.
Wait. R by 2. Sorry, sir. All are equal, sir.
All are equal, sir. We got the answer, sir?
Yes, sir.
Pakka na, sir?
Yes, sir.
Thank God, sir.
But from the surface.
Next question, sir. Two rings have charge plus q and minus 5q. Find the potential difference between A and B. So how are we supposed to find out the potential difference between the 2 points? First of all, we have to calculate the potential at point A. Potential at point A. Who are going to create potential at point A? One is this pink one and the other one is this green one. What is the potential due to the pink one?
Sir, at potential KQ by R, sir.
KQ by R minus root 5 KQ by the distance.
Root 5 R. Distance is root 5 R, sir.
Root 5 R. This is the potential at point A. What is the potential at point B? Due to the pink one, it will be equal to KQ by the distance will be root 2R. Yes or no?
Yes, sir.
Minus KQ by R. So minus 5 root 5 KQ by the radius is 2R. Do we understand how I calculated this?
Yes, sir.
This is the potential due to the pink ring and this is the potential due to the This is the potential due to the green ring. Everyone understands this, yes or no?
Yes, sir.
Once you know the potential, you can find out the potential difference by subtracting them. If a question comes on this category, the question would be such that The calculation would be simple. Do we understand this?
Yes, sir. Potential at A is 0. Sir.
Okay, whatever it is coming. It is coming 0. Good.
Yes,
Then potential at A is same as the potential difference between A and B is nothing but negative of potential difference of potential of B. Now this same question we had done it in terms of 2-point charges. Now one is a point charge and the other one is a ring, and I'll give you 2 minutes to give me the answer for this one. A point charge Q naught is placed at the center of a uniformly charged ring of total charge Q and radius R. If the point charge is slightly displaced with negligible force along the axis of the ring, find out its speed when it reaches a large distance. When it says large distance, that means infinity. So how are we supposed to do this? We can do this in many ways. I will do it by the law of conservation of mechanical energy from point A till point infinity. Total mechanical energy at point A will be equal to total mechanical energy at point B. What is the total mechanical energy at point A? It consists of kinetic energy and potential energy. What is the potential energy? KQ by R is the potential multiplied by Q naught. That is the potential energy. Yes or no?
yes, sir.
Plus the kinetic energy is 0. The total potential energy at infinity will be 0 and the kinetic energy will be equal to half mv square. From there you can calculate the value of V. Do you understand this?
Yes, sir.
Anyone got this answer?
Yes, sir.
Pakka?
Pakka, sir.
Okay, then this is the reverse brother of this question. You have a positively charged ring. The charge is not given. Let me take that charge as Q. Then you have a small charge, small q here. I give it a velocity v naught. What is the minimum velocity v naught so that the particle crosses the ring? Do we understand the question?
Yes, sir.
I'll give you 2 minutes to give me the answer. Mass of the particle is m if it is not given. So basically you have to apply block में. Let me call this point as A. Let me call this point as B. So I have to apply lock में from A to B. Total mechanical energy at point A must be equal to total mechanical energy at point B. What is the total mechanical energy at point A? KQQ
2 by.
root 2R. Yes or no?
Yes, sir.
That is the potential energy plus half m v naught square. That must be equal to, you have to find the minimum energy, minimum kinetic energy there, minimum velocity there. So velocity at this point must become 0. Yes or no?
Yes, sir.
Plus k q q by r. This is the energy at the center. Yes or no?
Yes, sir.
From here I think you are going to get v as under root of 2 k capital Q small q by mr 1 minus 1 by root 2. Did we get this answer? Yes or no? No, yes.
Yes, sir.
Last question for today is this. We have taken a lot of things today. Well done. A ring of radius r is having two charges in two halves. One half has plus q charge, the other half has 2q charge. Find the electric potential at a point 2 root 2r from its center. This question not going to come in JEE Mains. This is a question of JEE Advanced. And you have 2 minutes to give me the answer. What is the answer?
1 minute.
Remember, whether the charge is uniform or the charge is non-uniform, all the points on the ring are equidistant. What is the distance of any point on the ring from this point?
3R, sir.
3r. So what will be the electric potential? K into total charge is 3q divided by 3r. Do we understand this?
Yes, sir.
So the answer is kq by r. Do we get this?
Yes, sir.
Do we get this, everyone? Shall I move ahead? Just seen one more point, so you can just note it down as well. Again, for JEE Advanced, electric potential due to a disk at the point on the edge. So you take any point on the edge, point B or point Q or point P or point A. What is the electric potential at the edge of the disk? At the center of the disk, we know. What is the electric potential at the edge of the disk? The answer is sigma R by pi epsilon naught. Please remember this and note this down. Potential on the edge of the disk. Potential of any point on the edge of the disk. Do we get this? Have you noted this down?
1 minute.
Okay. That is the last point for this class. We have seen the meaning of potential and we have calculated a lot of things, potential difference. The next class we will see the relation between electric field and electric potential. So that will cover your electric potential and probably we will be able to finish electrostatics in a day or two. We have taken a good stride forward and we are moving with a very good speed and I'm very happy with this. If we keep on speed like this, I think I can finish your course by 15th of March, the entire one. But you have to keep up this pace. Okay, then I'll see you tomorrow. Take care. Have a nice day. God bless you all. Bye bye.
Bye, sir. Have a good day.
Bye beta.